I'm Professor Mark Sims. I'm part of the University of Leicester. I'm based at Space Park, Leicester. And sitting next door to me is John Holt, who's one of our senior engineers. We've both been in the space business a long time, and we're involved with an experiment called Fluorescent Deep Space Petri-Pod, which aims to fly worms in space to look at the effects of microgravity on biological organisms. Life on Earth didn't evolve to explore space, in particular human beings. We know there's all sorts of issues with human physiology in space, everything from your vision being affected to loss of calcium from your bones. Some recent discoveries where your eyesight changes, and believe it or not, the position of your brain within your skull changes as well. So we need to understand what the effects of microgravity are, and if you do it with a simpler organism, you might be able to disentangle the various effects of microgravity. And that led to John and with Tim from Exeter University, who's now at Ohio, thinking of an experiment to put worms into space, which we've now built and will get launched hopefully on April the 8th.
I can remember when I first met Tim, I think it was at one of the UK space conferences getting on for 8-10 years ago now, and he was talking about the worm stuff that he was doing and stuff that he was already doing on the International Space Station. And it kind of struck me with, you know, my background and stuff that I've done with Mark back on ExoMars with Life Marker Chip and other such things, that when we looked at the, I suppose what you might describe the research market in this field, people were developing, you know, their own bespoke pieces of technology, their own instruments, and it wasn't very long before, you know, I think Tim and I had a chat over a beer or something, and we then came up with the idea of having a sort of a generic, basic platform that you could use for worms, but equally you could use it for other things. You could put seeds in there if you're interested in looking at, you know, sort of, I don't know what you call it, exo-agriculture, that sort of thing, you know. And people are generally looking at, you know, can we grow food on the moon and other places? Could you put mammalian cells in there so you could have cell cultures? And obviously, could you have the worms, the C. elegans, you know, which is really the focus of Tim's research, and so that's the bulk of what's flying there. So really, it was the, you know, that's the application, but much more broadly, you know, there are lots of applications, and I think one of the visions that we always had was, you know, once we've demonstrated the technology, hopefully we do, fingers crossed on the 8th of April, you know, we put this thing on the ISS and then outside, you know, then start working with a much broader research environment, people from other universities, people from Europe as well, looking to see whether we can accommodate their experiments in space.
From John's initial lead, what we've done is we've engineered a demonstration unit that will go up to the space station. It will be in storage for a few days, then bolted to something called NREP, which is a platform from Voyager, who paid a commercial fee to get this experiment to the ISS. It's based around some little pods, which is why it's called the Fluorescent Deep Space Petri-Pod, and a optical camera and a fluorescent camera, which I'll talk about in a minute, and also some cells for some pods, I should say, for other specimens for test in orbit. So once it gets to the ISS, it will get bolted on the platform. It will be picked up from the Japanese airlock, and the platform will be mounted on the side of the space station, and it will sit there for at least 18 weeks before it's brought back in. The worms will be inside, and we were trying to take pictures of them and video. The device we've engineered has SD cards in it, so a lot of the video will actually be recorded on board rather than downloaded during the mission. And when the FDSPP, as it's called, comes back to Earth, which will be later this year or even towards the end of the year or even early next year, then we'll be able to download the data from the memory on board. what the team's done here is engineer a 12-pod system, 4 with fluorescent microscopes and optical microscopes, another 8 for things which will just be exposed to the space environment. And the idea of putting it on the outside of the space station is it will see more radiation. We built a radiation monitor into the unit, free from disturbance in terms of people moving the pod around and stuff like that. And consequently, it's probably a fairly good experiment to do as a demonstration. It's got fluorescent microscopes because C. elegans worms, which are these tiny little 1 millimeter worms which you find everywhere on Earth, have got fluorescent organs in their head, and the amount they wiggle tells you something about their health. So the idea is to take pictures both in visible light, which shows where the worms are, and then in fluorescent light to actually see these organs and see how well they're actually moving. Unfortunately, the worms don't know it, but it's a one-way trip for them because the little pods that are put in have got enough food in air for 15 to 20 weeks, perhaps a bit longer. But by the time they come back in, unfortunately, they will have run out of supplies.
But I think that's about their lifespan as well. I mean, I've got the sort of hand model here. That's about 0.5 centimetre diameter and about sort of 10 millimetres deep. So from a worm's perspective, that's almost like a little tiny space station for them. Yeah. It's like a self-contained life support spaceship for them, really.
Yeah. Yeah.
I have to say, I'm probably a bit jealous, actually. I don't know about you, Mark, but I've worked in space for 30 years now. You're a couple of years more than that. I would have loved to have been an astronaut, and yet here we are, taking some of the simplest animals on Earth and training them to be little astronauts.
The only thing they don't get is they don't get a window, so they don't get the great view.
I don't think they've got eyes.
No, I don't think they've got eyes, but it's been an interesting experiment because to design and build, because it has to go through various NASA safety reviews. That's been
a real challenge, hasn't it?
It's been a challenge, yeah, and we've changed some of the hardware to make the experiment more compatible with those safety things, but also to try and give better results. So, we've swapped from light emitting diodes to look at the fluorescence through to lasers, so you get a narrower band of light from it, which means you can get more detail. Now, we won't be able to get the video. We'll only be able to download 1 or 2 videos, but we will be able to get still images. And the idea is that the experiment is essentially, once it's powered up, is completely automatic. We can command it if we need to, but it will power itself up. It's got its own, each pod's got its own temperature and pressure sensors, so we know whether the pressure and temperature is right, that we don't lose any pressure. We've got lasers on each of the worm pods, and we've got the 4 cameras which look at the worm pods from above. So it's a great little experiment.
There's a lot going on there.
There's a lot going on, but it will be automatic. Once it's powered up, it will start a sequence of taking images of the worms, recording the video, writing that to the SD cards in the experiment, and then, as I say, we come back, we can download those videos. It's been, like all experiments, both fun and frustrating to work on. Fun in that if I talk to any of my friends about the experiment, they all get worms in space. They all love the idea of that. Frustrating in that the technical challenges, particularly on the software and the interaction with the space station, were a bit challenging at times, but we've overcome those, and hopefully everything will work once we get to space.
It's interesting. On the one hand, I suppose the technology is actually quite simple. It's cameras, it's doing fluorescence imaging, laser diodes, sort of thing that you've got in a CD player or DVD player at home, all of those kinds of things. So on that side, it's, there's the simple part of it, but it's actually really quite challenging, getting the package right, getting it small, making it work in the space environment. And unless I'm wrong, until recently, as far as I'm aware, nobody has actually done an automatic fluorescence microscopy experiment that can sit outside of the International Space Station. So lots of fluorescence imaging has been done on the ISS. Tim's done that sort of thing before, and they've got fluorescence microscope. But having a little tiny package, which is probably, what is it, 30 centimeters
30
long,
centimetres by 10 by 10.
Yeah. So really quite small. Having 12 altogether, isn't it? Little tiny experiments inside of there, 8 of those being fluorescence imaging. That's the first time that's been done remotely in space. So that's really quite an achievement, I think.
Yeah, it's interesting from a safety point of view in that we had to design it so it could survive an accidental kick by an astronaut.
I remember that, yes.
EVA.
Yes. Yep.
Had to get the mechanical design right, had to get the thermal design right. And in particular, it's interesting that lots of experiments which have flown on that platform, nobody's really worried too much about the temperature. And we have the
and
issue.
how stable it was.
Yeah, how stable it is. And we have the issue that if we get the worms hotter than 22 degrees, they die.
They don't like that, do they?
And we have to keep them cool from the day they're installed, which is roughly 2 days before launch until they're outside the space station. And they've got little heaters built into the unit to keep them at a temperature somewhere between 8 degrees and 20 degrees. It will vary a bit as the space station goes around the Earth. We didn't engineer in a very complicated heating system because we wanted something which was simple and reliable and couldn't go wrong and didn't have lots of software interfaces. Yeah. In order to get FDSPP built and tested and ready for launch, it's taken a team of engineers, myself as project manager, building on the work that John and Tim did in the early days to make the system and assemble it. And that's involved electronic engineer, it's involved a mechanical engineer, and it's involved what we call a systems engineer, which looks at the overall concept, a couple of junior engineers to assist them, somebody and two experienced software engineer and a junior software engineer in order to get FDSPP together and ready for launch and test it. And a lot of that's come from particularly the hard work of the electrical engineer, Duncan Ross, who did a lot of the took the initial mechanical design from John and Tim and turned it into something which we could reliably put together and use. And we put in some innovations from the original thing, like having a radiation monitor, so we can measure the total dose in the experiment over the period. That's a solid state device which accumulates radiation damage, and it changes its characteristic in terms of current and voltage, and we can measure in real time what the dose is. It's going to the laser rather than LEDs in order to get a really sharp fluorescent response from the worms. Put in the appropriate laser filters in there. Though the laser did actually cost us a bit in terms of safety, to make sure that the laser can't shine out of the box and be able to dazzle an astronaut. So we had to put a shield within the box to protect from that occurrence. And because there is a hole in the box in order to vent the gas once we get to orbit, you don't want the thing blowing up like a balloon and distorting and damaging itself. So there's a vent, and we had to put a shield behind that to make sure that no laser light could shine out the hole and affect an astronaut, particularly astronaut outside on EVA. And as I said, separately, we also had to engineer it such that it would take glancing blow from an astronaut's boot in the side of the experiment. That involved a lot of mechanical analysis by our mechanical engineer and team in order to do that. And then you have to document it all. It has to go to NASA and go through a series of safety reviews. And because it's got working electronics in it, you have to make sure it won't interfere with anything on the space station. So it went to Marshall Space Flight Center in Alabama for what they call electromagnetic compatibility test, which it passed flying colours, where the experiment was powered up, and they looked at the emissions from the experiment to make sure it was below levels which would either damage the space station and, in our case, affect the noise coming from the space station, affect the operations of FDSPP.
I mean, we've talked a little bit about the history of FDSPP, where it came from. There's actually been several different funding streams that have come from the UK Space Agency to get the technology to this point. The most recent one came about at the end of 2023, and that was Tim Etheridge and I. We put that proposal together to UK Space Agency, and initially, and this is just before you got involved, Mark, as well. We were looking at flying this on a CubeSat, and it turned out that there were a number of complexities with that. Needing high gain antenna, actually finding someone that could provide us with a commercial CubeSat to put the instrument on. And it came about actually, and I can remember Tim and I being completely shocked by this, that to put something on the International Space Station was cheaper than a commercial CubeSat. I don't know whether that's still the case, but that's why we ended up going the route of the International Space Station. And I suppose really that's where Tim and I had, because we had built a previous flight model to fly on a CubeSat, and that didn't happen. Various things fell apart. It was also involving a Russian launcher, and so there were problems there. And so it kind of changed direction completely once we realised the cost difference, and I suppose that's where we ended up to where we are today.
And the UK Space Agency was good enough to fund that cost, and that led to the commercial route, because there was company Voyager, which nanoracks, as they were previously, which John and Tim had dealt with in the past, who had the ability to fly experiments and put them on the outside of the space station on their so-called NREP platform.
I think one of the big benefits that's come out of this, and one of the things that we've shown, is that when you've got the right team, project manager, engineer, scientists, technicians, software engineers as well, people talk about space becoming more accessible, they talk about space getting cheaper, and more people getting involved. Back in the day when I started in space, these were multi-million-pound projects, and for good reason, and research projects, the big research projects, like Rosalind Franklin, which is hopefully going to go very soon as well. Obviously, they're going to be expensive projects because they're technically demanding, normally working in a much more hostile environment, in the case of Rosalind Franklin on the surface of Mars. But for getting access to the International Space Station and doing experiments, for not a lot of money, at well under £500,000, we've been able to put an instrument together. We've been able to do the development work. We've been able to collaborate with people in other institutions, and that covers the cost of the flight. That covers the cost of the astronaut handling it on the ISS, putting it outside, and then the thing coming back as well. And I think that says something about the way that the UK Space Agency is working, and the way that they're managing, their sort of research projects as well, to get a really good, what's the word I'm looking for, good value for money, for what is taxpayers' money. So in this case, it's, a complete package, a really good piece of science, data at the end of it. And as we said earlier on, it's also a science first, because nobody, as far as we're aware, has ever done automatic fluorescent microscopy outside of the International Space Station, or having a package that you could put on a CubeSat, or even you could send it to the moon if you wanted to. And there's some of the other crazy ideas that we have for the future. We do a lot of work actually with Open University and in particular Professor Karen Olsen-Francis. So one of the experiments we're flying, it's not a worms one, she has some little tiny microorganisms which are dried down onto what looked like a little tiny filter paper, you know, a couple of millimeters wide, 8 millimeters long. So one of it was a later addition to the package to put them into one of the pods so that they can then be exposed to the radiation environment, because, you know, there's a lot of wanting to understand, you know, not just worms and, you know, sort of bigger organisms, how they respond in the microgravity environment, but how microbes do as well. That's obviously really important for, you know, controlling astronaut health in terms of infection and bacteria and other sorts of things. So yeah, we're flying one of her experiments, and that's we're not doing any imaging of that, but that's one of the big advantages of two things really. One is the flexibility of the platform, which I think is really quite impressive, but the fact that it's coming back as well. So Karen will be able to get these organisms back and then analyse them and see how they've responded and reacted to the microgravity environment and the radiation environment there as well.
We're also going to fly some quantum dots, which are a way of
That's right, yeah.
marking biology, making things glow, and just to see how they survive. There won't be anything attached to them, but it's a precursor for future experiments. And what we very much like to do is take this first generation and slightly re-engineer it, so there's actually a fairly simple life support system in there so that we can keep the worms available for longer, alive for longer, and also have other organisms in there. In particular, what you'd like to do, of course, is bring organisms back and look at the genetic changes. And there you do actually need to keep things alive. We're not the only people planning experiments like this. Other people both in the UK and abroad are planning experiments like this, but this will be, we believe, the first commercially paid for experiment on microgravity on C. elegans worms in orbit.
It's interesting to say about, you know, thinking about the future. I alluded to earlier on, there's a lot of people within Europe, you know, so one of the reasons that, you know, Karen and I got together and talked about could we do this exposure experiment is because at the moment there's a need within the space community to be able to do exposures relatively quickly and I'm going to say relatively cheaply as well. I mean, we can touch on the cost, you know, of this project in a moment, but you know, being able to have that flexibility, there are probably that I know of about a dozen research groups within Europe who are desperate to fly something like what we're doing with FDSPP at the moment. Most of them don't even want to do imaging or anything. They just want to put the thing outside, open the lid, do an exposure for a period of time, a week, a month, whatever that might be, close the lid, and then bring it back. So that's what we're doing with the OU. That'll be, I suppose, a bit of a trial to see how well the system works in that respect.
Well, the only difference is we're not opening the lid on FDSPP. The pods will be sealed inside, though in actual fact the inside of the container will be vacuumed, and in order to retain the pressure in the pods we've got multiple O-rings to...
It's a double seal, isn't it?
It's a double seal, top and bottom, to make sure that we don't leak air. We've done things like vacuum tests on that. We've done some vibration tests to make sure that the pods will survive launch without disturbing the O-rings and then consequently leaking. So in a moment it's a bit of crossing our fingers and hoping it all works on the day. As I say, the worms will be installed roughly 36 hours before launch. The FDSPP will then be put into, will be chilled with some cooling packs to keep it cold, go up to the space station, be unpacked by the astronauts, put back into cold storage until they can actually assemble it onto NREP, which hopefully will be within a week or so of arrival at most. put into the Japanese airlock, put outside, and then plugged in when the NREP is plugged to the side of the Japanese exposure module, and then hopefully we start getting data, and we'll be able to see that data back here in the UK. It will flow via Voyager systems in the States, but I think mostly via Houston, and we'll see what we get from the mission.
I was going to pick up on the, because you mentioned double seals there, I mean, for both you and I, that's a challenge that's haunted us probably for a decade or more, working on various life sciences projects going into space, and particularly with a Mars focus as well, which is probably where a lot of my research is kind of focused. So going back again many years, it's actually really dangerous when you put a couple of scientists together in a pub over a beer, because the beer mat comes out and you start coming up with these crazy ideas. And one of the things Tim and I were looking at, back in the early days, was there was talk about doing I think it was a Phobos sample return mission. We also spent a lot of time on the acronym as well. And so there's actually two names that kind of float around for this project. One is FDSPP, which is Fluorescent Deep Space Petri-Pod. And then there was WORMS, and we kind of crowbarred that acronym to be Worms on Returned Mars Mission, or something like that. And the idea being is, because now that humanity is expanding out into the solar system, obviously with Artemis and going back to the moon, and NASA doing all of that, with the idea of then, moon to Mars kind of human exploration, that if there was something like a Phobos sample return mission, you could have something very similar to this. You could put different organisms in there with the intention that they're coming back. And then you can understand that deep space environment, and that's work that's never been done before, what that deep space environment would have on whatever organism you chose to go into your package. Now, this is a very convoluted way of getting back to the double seals. So there's a thing that is often talked about in kind of this planetary science field, which is planetary protection. So it's about protecting our planet if you're bringing stuff back from Mars or some other planet, but also being responsible, doing responsible science and protecting the solar system as well. And so the idea of the double seal was that if you did have some sort of microorganism that went to Phobos or somewhere like that, and something went wrong and it wasn't coming back, that you have contained your terrestrial organism so that it doesn't get out, so that you're not contaminating that celestial environment.
And that double seal fed across to FDSPP, or WORMS as it's been, as you say, it's been called in the past. And that is one of the basic technologies. Though for the future, if we want a little life support system in there, we might have to look at other technologies in order to get the organisms in and out safely. Yeah. But it's now sit and wait until we can put the worms in and get them into orbit. So go worms for space.
Absolutely.